master is he who keep you from falling and suffer defeat. If you call on me in your greatest time, is it you?
Good day, grade 11s. Today we have another video on the March. This is the March controlled paper. It was written last term by the grade 11s from one high school. So we are going to look at the paper and we're going to answer the following questions. I think there are around like 8 questions. So we are going to do part 1 for question 1, part 2 for question 2, and so on and so forth. So let's now zoom in and look at the paper. You have now question 1, which is a multiple choice question. So let's read the question. The question says, you have various options provided as possible answers to the following questions. Each question has only one correct answer. Choose the answer and write only the letter. So now let's look at 1.1. For 1.1, the question says, which one of the following represent a vector quantity and a scalar quantity? So we want a quantity that is a vector and a quantity that is a scalar. Now, before we go to the questions, what is a vector? A vector is a quantity that has magnitude and direction. So a scalar is a quantity that has magnitude only or a size only. So let's look now at the options. Option A, we are given a displacement and a velocity. Now a displacement is a vector and velocity is also a vector. So it cannot be option A because this is a vector and we are looking for a vector and a scalar. Option B says acceleration and force. Now acceleration is a velocity, a force, acceleration is a vector and a force is also a vector, so it cannot be option B. Now let's go to option C. A mass, we know a mass is a scalar, and mechanical energy, we know energy is also a scalar, so it cannot be option C. Now let's look at the last one. The weight, a weight is a vector, and time we know it's a scalar. So this is our option, which is option D. That is the answer for 1.1. It's option D. So let's move on to the following question, which is question 2, 1.2. 1.2 says, which one of the following forces cannot be equal to 0? Okay, now let's look at the options. Number 1, they said the normal force. Remember, we are looking for a force that cannot be equal to 0. Now, can the normal force be equal to 0? Let's look at the situation. Let's say, for example, we have a surface. Remember, by definition, the normal force is the force that the surface exerts on the object, and that force is always perpendicular to the surface. Now, if you have a surface, maybe it can be a table, and you put a block on top of a table. Now, this block, we know it has a weight, and the table is going to apply or exert a force on that block. Now, the normal force in this situation is equal to the weight. That's why the table is not breaking off, because this normal force is equal to the weight. Now imagine a situation whereby now the block now is above the surface. So if the block is above the surface, that means now the surface is not exerting any force on the block, and then we say the normal force will be equal to zero. The normal force will only be equal to the weight when the block is in contact with the surface. So that proves that the normal force can be equal to zero. So the answer, it cannot be option A, because the normal force can be equal to zero. We are looking for a force that cannot be equal to zero. Now let's look at option B, the frictional force. The frictional force. Now, the frictional force, let's say, by definition first, what is the frictional force? The frictional force is the force that opposes the applied force or the motion of the object. So if you have an object that is being pulled by an applied force, let's say it's being pulled to the right. Now, if this object or the block is moving, if it is moving at a constant velocity, if it is moving at a constant velocity, that means that the applied force will be 0 Newton. In a situation where the object is moving at a constant velocity, the acceleration, we know, is always 0. Now, if the acceleration is 0 meters per second square, that means the applied force is 0 newtons. Now, by definition, a frictional force is a force that is opposing this applied force. And in a situation where an object is moving at a constant velocity, the frictional force will be equal to the applied force. So, and also in a situation where the object is stationary, so we say the kinetic frictional force is 0 in a situation where the object is stationary, and also in a situation where the object is moving at a constant velocity. Since the frictional force is equal to the applied force, so the frictional force will be equal to 0 Newton. So in both situations, the frictional force or the kinetic frictional force can be equal to 0. So this cannot be the answer. Also, we already answered for option D, because it's talking about the applied force. Here we just proved that the applied force can be equal to 0 in a situation where the object is moving at a constant velocity. So that means option B is falling out and option D is falling out. Now let's look at option C, the gravitational force. Can the gravitational force be equal to 0? That's what we want to check for the gravitational force. Now, a gravitational force, we know it's the force that the object exerts towards the center of the earth, and this force is mg, where the mass is constant throughout. Even if this object was falling from that position, this force would be mg. Even if it hits the ground, the force would be mg throughout the projection of the ball, or the falling of the object. So this g, we know it's 9,8. So the gravitational force cannot be equal equal to 0, because throughout, whether it's above the surface or it's hitting the surface, the force will always exert the same magnitude. So the f of g, or the weight, cannot be equal to 0. That is option C. So option C is the answer for 1.2. The gravitational force cannot be equal to 0. Okay, now for question 1.3, the question is saying a girl weight 600 Newton, a girl of weight 600 Newton is standing on a bathroom scale in a lift that is moving, and she noticed that the scale reads 560 Newton. A girl of weight 600 Newton standing on a bathroom scale in a lift that is moving, then the scale reads 560 Newton. Which one of the following is correct conclusion about the motion of the lift? The lift is accelerating upward, accelerating downwards, moving up at constant velocity, or moving downwards at constant velocity. So now we have a lift problem. So before we answer now this question, let me give you a simple explanation on how to answer this question. I have a simple example here. We have a girl that is inside the lift. In this case, now the girl has a mass of 20 kg, and let's say the weight of the girl is 196 newtons, and the girl is standing on a scale inside the lift. So there are two forces that are acting on this girl. There is a normal force, which is the force that the scale exerts on the girl. There is also a weight, which is the weight of the girl. So the reading on the scale will always be determined by the value of the normal force, because the scale will only have a value or a reading when the girl is in contact with the scale. So if the girl is like above the scale will not read any value. The girl must always be in contact with the scale, then the scale will give a reading. So that means that the scale is reading the value of the normal force. So let's look now at the Newton's second law for this situation. The sum of the forces that are acting on the girl, let's take up for example. Let's say up is positive. So we have the normal force, which is positive, minus the weight, which is negative, equals to ma. So the normal force, therefore, is equal to the weight plus ma. So this is the formula for the normal force. Let's expand it further. We say the normal force will be equal to mg plus ma. So this normal force is a reading of the scale. So now we are going to look at three situations to determine the reading of the scale, which is the value of the normal force regarding the girl on the scale. For situation number one, let's say that a lift is at rest. The lift is just stationary and a girl is standing on a lift. What would be the value of the normal force in that situation? So if we apply this formula for all these situations, we can determine the value of the normal force. If we say the normal force is equal to mg plus ma for this situation, Now, for a situation where the lift now is at rest, if a lift is at rest, we know the acceleration is 0 meters per second squared. So that means this acceleration would be 0. And if the acceleration is 0, then we know that the normal force will only be equal to mg. And what is mg? We say mg is the weight. So that means that this normal force will read the value of the weight of a girl, which is 196 Newton. So in a situation where the lift is at rest, the normal force is equal to the weight. So in this case, the normal force, which is a reading of a scale, will be equal to the weight. That is when the lift is at rest. The normal force, which is a reading of a scale, will be equal to the weight. That is example number 1. Now, before we move to when the lift is accelerating upward or the lift is accelerating downward, what happens if a lift is moving at a constant velocity? Let's say the lift is moving upwards, but it is moving at a constant velocity. So if it is moving at a constant velocity, still we know the acceleration will be 0. That means it will be the normal force, which is the reading of a scale, will still be equal to the weight. Even if the lift now is moving downwards at a constant velocity, still the normal force will be equal to the weight. Why? Because the acceleration is 0. So in all three instances, whether the lift is at rest, whether the lift is moving upward at constant velocity or moving downward at constant velocity, the normal force will be equal to the weight. But what happens now if a lift is moving upward and is accelerating upwards? Now, not at constant velocity, but is accelerating upward. Now, acceleration by definition, we know it is a rate of change of velocity. So that means that if a lift is accelerating upwards, it is gaining speed per second. Let's say in this case, it's gaining a speed of 1 meter per second squared. The acceleration is 1 meter per second squared. So that means this lift now is moving up, is gaining speed of 1 meter per second squared every second squared. So let's apply now this formula for the normal force, which is M equals to mg plus ma. So we want to see what will be the reading now of the normal force, which is a reading of the scale when the lift now is moving up or accelerating up at 1 meter per second squared, is gaining speed every second of 1 meter per second squared. Now, this acceleration now is positive. The acceleration now is positive. So what you will have in this situation, remember we said the mass of a girl is 20 by 9.8. Okay, for the purposes of space, let me just take out the common factor, which is the mass, because I don't have space here. So we have G plus A, just to save space. So we are saying that if this acceleration is like 1 meter per second squared, imagine now you have 1. So What you're gonna have in this situation, you're gonna have the mass, which is 20, multiplied by 9.8 plus 1, which is 10.8. 9.8 plus 1 is like 10.8. Now that will give you something like 216. I think so. Now, in a situation where the lift is moving up, accelerating upwards, we see the rhythm of a scale is greater than the reading on the weight of a girl, than the actual weight of a girl. The normal force in this case is greater than the weight of a girl. At a situation where the lift is accelerating upward, the scale will going to read a value that is bigger than the actual weight. Now, last example, what happens when we have a situation now a lift is accelerating downwards? That means that it is losing speed as it moves downwards. This is the lift moving downwards. It is losing speed now. It is not gaining speed, it is losing speed. So in this situation, let's look now at the value of the normal force. At the value of the normal force. Okay, let's say plus A. Now, because of it is losing speed, you're going to have a situation now where A is like it's negative. Then the normal force will be 29.8 minus 1. It's like you have 8.8. And then when you punch that on the calculator, you're going to have something like 176 newtons. So you have like 176 newtons. Now the reading on the scale in the situation where the lift is accelerating downwards, you can see now that the normal force is having a value now that is less than the actual value of the weight of the girl. So the reading on the scale would be less than the actual weight of a girl. So let's summarize what we just said here. We said if the lift is at rest, the scale value will be equal to the actual weight. If it is moving or it is accelerating upwards, the reading on the scale will be greater than the actual weight of a girl. If it is accelerating downwards, the reading on the scale would be less than the actual value of the weight of the girl. Now, one more option. What happens now if the cable of the lift now starts to break? Let's say this lift had a cable, and now the cable breaks. Now, in the case where the cable breaks, and let's say it was on top and starts to break, and the lift now begins to fall. In that case, we say both the lift and the girl are falling, they are at free fall. Now, at free fall, that means the speed at which the girl would fall would be 9.8 meters per second, and the speed for the lift would also be 9.8 meters per second. So in that case, you're going to have something like this. You're going to have something like this. The normal force now would be 9.8 minus 9.8. 9.8 minus 9.8, that's a 0, which means the normal force now would be 0 newtons. So there will be no reading when the cable of the lift suddenly breaks. So these are the four situations on the lift problems that you're gonna have on your multiple choice questions. So going back now to our question. So the question now was saying a girl of weight 600 newtons is standing on a bathroom scale. So the weight now is 600 newtons. But the scale is, which is a normal force reading, is 560 newtons. So we can see that the normal force now, which is a reading on the scale, is less than the reading the actual weight of the girl. So in our previous explanation, we said in a case where the reading of the scale is less than the actual weight of a girl, we know this is accelerating downwards. We know it is accelerating downwards. So that is what you know from your knowledge, from your previous example. So let's look at the option. Option A, accelerating upward, no. Accelerating downwards, yes. Moving at a constant velocity, no, because if it was moving at a constant velocity, we know then the reading of the scale is supposed to be equal to the weight. So moving downward at a constant velocity, no. So the only option we have now is option B. So every time you have a big problem, just apply this knowledge. Now let's move to the following question. Okay, 1.4, which one of the following represent a relationship between the gravitational force F between two objects and the distance r between the objects? Now, before we go to the graphs, let us remind each other about the Newton's universal gravitational law. So we know that when you have two objects, let's say this is object 1, this is object 2, and you have a distance between them, we say that if the distance between two objects is less or short, the force is going to be greater if the distance is less. But the force between two objects will be less if the distance between them is greater. So you can see that the force and the distance between two objects is inversely proportional. When the distance decreases, the force increases. When the distance increases, the force decreases. So this is a relationship that is happening here. The force and the square of a distance is inversely proportional. That means when the other increases, the other decreases. So if you are going to have a situation where you're not talking now about the square of a distance, you are talking now about the inverse. The inverse of a distance. What will be the relationship here? So remember, if f is inversely proportional to the square of the distance, if you have now, let me put it here, we say f is inversely proportional to the square of distance. But if you have now the inverse of the square of a distance, so what we do, we know that we have to flip this over to become r squared. So if you flip this over from 1 over, I think in maths, I'm not good in maths, If you have 1 over r squared, we know that we flip this over to be r squared over 1. So then you have f is directly proportional to 1 over that inverse. Okay. Okay, let me quickly show you here. Here I said if you have a distance, in this case, which is 2, I increase it to a 4, I increase it to a 6. So you see my distance is increasing from 2, 4, and 6. What happens now to the force? You see the force is 0.25 newtons, which is less 0.0265. When you increase the distance, the less is decreasing. When you have a greater distance of 6, the force is decreasing from 0.0625 to 0.027. From 0.0625 to 0.625 to 0.027. So when you increase the distance, the force is decreasing. You increase the distance, the force is decreasing. You increase the distance, the force is increasing. So this is what we said previously. When the distance increase, the force decrease. But now what happens if you put the inverse of the distance squared? So in this case, I have like the inverse, which is 1 over 2. Then what happens to the force? It becomes 4. So I increase that distance now to a quarter. The force also increases. I increase this distance now to the inverse of a distance, which is 1 over 6 squared. The force also increases. So if you put the inverse of a distance and you increase the inverse of a distance, the force will always increase. So we say in this situation that the force will be directly proportional to the inverse of the square of the distance. Yeah, this is what I wanted to explain to you, that when you have a distance and then you increase it, the force will decrease. But when you have the inverse of a distance squared, the force will also increase. Yeah, that's what I wanted to explain. So let's go to our graphs now. They said now, let's choose between the gravitational force and the distance from the following graphs. So we have a relationship of the force and the distance. So for option A, we have the force and the inverse of a distance. This graph is not true because of it says the force will be constant as the inverse of a distance increases. Now, what about this one? We have on B the force, and you have the inverse of a distance squared. This is also not true because I've shown you previously they are supposed to be directly proportional. So for option C, you have the force and also have the inverse of a distance squared, and it is directly proportional. Then we know this one is true. This one is not true, so we always take option C. Yeah, that's the answer for 1.4. Okay, so in 1.5, they say the same force with magnitude F is applied to two identical blocks on the same surface as shown. Both blocks move to the right. So we have block P and block Q. They have the same amount of mass. They are identical. Now block P is pushed by this force to the right, and block M is pulled by this force in the diagonal direction. So the question says, which of the following will be the same for both blocks? The acceleration, or the kinetic frictional force, or the ratio of the kinetic frictional force to the normal force, or the normal force. Which one will be the same? We have to choose now from these 4 options. Now, before we choose from these 4 options, Let's quickly try to explain what's happening here. So we have this block, which is block P. Remember, there was a force pushing it on that side. Then we have the second block, which is block Q, and there was a force that was pulling it in that direction at a certain angle. So if you look at block P, for block P, if you do a little free body diagram, here there is a force, then we know this is the normal force. This is the normal force of the normal force of the surface towards the board, the block. Let me just do F and N because I'm only going to need these two. Okay, let's also just do the weight. Okay, so let's do the normal force on this one, the free body diagram on this one. So this is the force, which is diagonal, and then this is the normal force. This is the weight. Okay, let's also put the friction here. This one, the friction will be on the opposite side. I'm not going to do the friction on this one. Okay, so for block Q, we know that when you have a force that is diagonal, that force has two components. It has like F of X, the horizontal component, and F of Y, which is a vertical component. So for the acceleration on block P, the sum on this one would be F net equals to MA. Then the friction on this one is in opposite direction to the applied force, like the friction is moving that side. So the acceleration now for block P. Let's look at the acceleration for block P. There are two forces here. The force applied is to the right, the friction is to the left. So if you want to check the acceleration would be equal to F minus the kinetic frictional force divided by the mass. But let's look at this one, the block Q. If we do the second Newton law on this one, we have now the horizontal force, which is F of X minus the kinetic frictional force equals to acceleration. So the acceleration on this one would be F of X minus the kinetic frictional force divided by the mass. So we can easily see that this acceleration is not the same as this acceleration, because here we have a constant force F. Here we don't have F, but we have a component of F, which is a horizontal component of F. So that means that option A cannot be the answer, because we want here an option where we will have the same for both. So the acceleration for P won't be the same for Q. Now let's look at B, which is the kinetic frictional force. The kinetic frictional force, is this kinetic frictional force going to be the same as that kinetic frictional force? Okay, let's use the same example. Okay, the kinetic frictional force has a formula, that is the kinetic coefficient multiplied by the normal force. So let's also write here the kinetic frictional force is equal to the kinetic coefficient multiplied by the normal force. So for block P, what is the normal force on block P? On block P, the normal force is equal to the weight. So we can easily say here that the normal force is equal to the weight, which is mg, because the weight is mg. So this is the kinetic frictional force for block P. Now let's look at block Q. What is the kinetic frictional force here for block Q? So what is the normal force? Now, we cannot say here the normal force is equal to the weight because there is also another component, which is another force, which is a vertical component of F. So in this case, the normal force minus the weight, okay, let's say plus F of y minus the weight equals to 0. I'm looking at the vertical forces. If let's say I take up as positive, so the normal force plus F of y minus the weight is equal to 0. And the normal force on this one, I take F of g to the right, it's going to be positive. F of y to the right is going to be negative. So I'm having something like the normal force is equals to mg minus F sine of theta. So you can see this normal force is not the same as the normal force. The normal force for P is this one. The normal force for Q is that one. So the kinetic frictional force for P won't be the same kinetic frictional force as P because of the normal force of the two are not the same. So we say now for B, it cannot be the option. For B, it cannot be the option, so we don't take B. Now, for D also, because they said the normal force, we said the normal force is not the same as I showed you, that the normal force here is mg, the normal force here is mg minus F sine theta. So it cannot be option D either. So we are left now with option C. Let's read the ratio of the kinetic frictional force to the normal. What is the ratio of the kinetic frictional force to the normal? If the frictional force, kinetic frictional force is equal to the kinetic coefficient times the normal force, now the ratio of this, the frictional force to the normal, is my kinetic coefficient. So that means that the kinetic coefficient here is still the same kinetic coefficient there. Why? Because of they are both moving at the same surface. So they are both moving on the same rough street. So it's the same street. So the kinetic coefficient will be the same for block T and for block Q. So the answer is option C. Okay, so question 1.6 says two identical neutral metal spheres P and Q are placed on an insulated stand. They are brought into contact with each other and a charged rod is brought near to sphere P as shown in the diagram below. After the spheres have made contact, they are separated, and it was found that electrons were transferred from P to sphere, from sphere P to sphere Q. Which one of the following concerning the charges on the two spheres is true? Okay, now let us look at this one. So imagine that you have two charges. This is charge, this is sphere P, this is sphere Q. So they are said to be in contact with each other. As you can see, they are in contact and they are both neutral, which means they have the same equal number of charges. So if you brought a charged rod near sphere P, so this is a charged rod. So let's say it is filled with negative charges, which are electrons. So this charged rod now that is brought near sphere P, the negatives on the rod, the negative charges on the rod will repel the negative charges on sphere P. And those electrons would be moved to charged Q. because they are repelled from P by the negatively charged rod. So eventually you're going to have now rod or sphere P with more positives, and you're going to have now sphere Q which has now more negatives than positives. So because of that rod that was brought in and it was removed. So that's why they said electrons were moved now from P to Q. Why electrons were moved from P to Q? Because of the charged rod which has negatively charged particles that moved or repel these ones to P. So now we're going to have now sphere P as more positive and sphere Q will be now more negative. So this is a situation that is going to happen if you brought a charged rod close to sphere P. P would be more negative and P would be more positive, and sphere Q would be more negative. So let's go to the options now and see the option. It cannot be option A because it says here that P is positive, Q is positive, so it's not this one. P is positive and Q is negative, that's that one. Negative and negative, that's incorrect. Negative and positive, that's incorrect. So the answer for this one is B. That is 1.6. Now the last question, which is 1.7. 1.7 says 2 point charges Q1, Q2 are separated by distance R and experience an electrostatic force F. The charge on Q1 is doubled and the distance between the charges R is also doubled. State the new value of the force the charges experience in terms of F. Okay, so Q1 is doubled and the distance R is doubled. Okay, let's look at this one. So the formula of the electrostatic of the Coulomb's law says K is equals to F is equal to K Q1 times Q2 over R squared. So they said now that Q1 is doubled. So Q1 is doubled, I'm going to put a 2 there, and the distance is doubled, I'm going to put a 2 there. Then I'm going to make everything else become constant, like 1. So I'm going to have 1 times 2 is 2 times 2, that's 2, over 2 is squared, that's a 4. And simplify this fraction, 2 divided by 2, that's 1, 4 divided by 2, that's 2. So meaning to say that the force in terms of, this will be the force that the charges will experience in terms of F is going to be 1 over 2F. So obviously that's A, it cannot be B, cannot be C, cannot be D. So the answer for 1.7 is F. In other words, if you double the charge and you double the distance, then the charge, the force, it decreases because of the distance now is being increased, it's being doubled. So the force now we know is going to go down. All right, that was the last question for the multiple choice. Now we're going to go to the next video, which will be the question 2 of the test.